Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to really dive into this idea of rates of reaction and kinetics. So when we're trying to look at how a reaction proceeds with time, one of the first things we want to try and do is analyze, well, the rate. So this is essentially going to be a way of talking about how quickly a reaction goes. So for that, we need to develop some standardized language. So I'm going to be describing rates of reaction just with the simple word rate. However, some textbooks and resources will use the Greek letter nu to really illustrate that this is a speed that we're talking about. And one of the simplest ways we can analyze rate is just simply seeing how many moles of reaction, again, accounting for stoichiometry, which we'll talk about in a bit, occur in a given amount of time. However, one of the things that is a little bit pesky is that when we're looking at aqueous reactions, one of the big things we're going to be doing is instead of monitoring just the overall species, we're going to be looking at moles of the overall species, we're going to be looking at molarity. So we'll track either the concentration of reactant or product, and occasionally for gas phase species, you can also use pressure. So as we look at these various species, since the volume of the reaction shouldn't change, again, molarity is a very easy way to talk about these species, and it's often easy to measure through things like spectroscopy. So one of the other things is that we need to account for stoichiometry. So if I end up generating reactants, or generating products, I will be consuming some stoichiometric equivalent of reactants. So the first thing we really need to pull out of the way is when looking at rates, just acknowledging stoichiometry. So let's do this by looking at the oxidation of tin 2 plus by iron. So if this reaction essentially occurs and we end up increasing the concentration of our tin 4 product, so this is our oxidized tin, by about 30 millimolar over, say, a half a minute, what would we expect to be the average rate? So for this, we can do simple change of concentration over change in time. So if I increase by 30 millimolar in 30 seconds, that means my concentration goes up by about 1 millimolar, which, is a fair bit in a single second. Now, here's the thing. If I know exactly how much the concentration of my tin is increased, I can use this same idea to figure out how the concentration of my iron is increased. So first of all, it should increase, so we should have a positive number. And for every 1 tin I make, I should be making 2 irons. So I should have double the rate. And again, we see this with the stoichiometry. I make twice the concentration of my iron species. So this means that I'd expect to be producing my iron at about 2 millimolar per second. So what we can do is relate this to an overall change in rate. So how many molar what's the molar change of the reaction? So for this, it's most convenient to identify a species with a stoichiometric coefficient of 1. So the change in concentration of tin should be the change in the concentration of reaction. However, this gets a little peskier if I'm measuring the change in concentration of iron, because it will be twice the size of the rate of the reaction, again, because of that coefficient. So to bring it down to size, we have to divide that change in concentration by the coefficient to find the moles of reaction. So the overall rate of reaction would be about 1 millimolar per second. However, we aren't just generating products, we're also consuming reactants. So what would be the average change in my tin 2 plus concentration? So most notably, again, this will be the change in tin over time. Again, if we produce 0.03 molar of the tin, this means tin 4 plus, I'll be consuming 0.03 molar of my tin 2 plus. So we'll have the same general rate of 0.001 molar, or 1 millimolar, but now we have this negative sign because the reactant concentration is decreasing. We can do something very similar for iron. Again, concentration is decreasing, but again, at twice the rate of the tin. So we have a decrease of about 2 millimolar of iron. So what we can do is also relate this to the rate of reaction. Our rate of reaction is still going forward positive at 1 millimolar, but the big difference is that the amount of tin should be decreasing and the amount of iron should also, again, be decreasing. So again, watch out for these negative coefficients. Since I've got a negative change in tin, I need to cancel that out with the coefficient. So we can expand this to a more generic sort of reaction. Some amount of A plus some amount of B makes C and D. Now, I can go ahead and track the rate of a reaction using any of these concentrations. However, for the reactants, again, since that concentration should be decreasing, I have to use the negative sign to make sure I maintain a positive rate of reaction. Also, say if I'm consuming 4 A's per mole of reaction, I'm going to have to divide that change by 4 just so that everybody's equalized. So in order to find the rate of reaction, take the change of any given species, divide by the coefficient, and again, if it's a reactant, put a negative sign out front. If it's a product, it's fine as is, because that rate of reaction should always be positive, and that stoichiometric coefficient helps equalize essentially rates of production and consumption. However, one of the things that we often end up doing is using these stoichiometric coefficients instead of trying to follow all of the various species over time. We can follow one single species and use that to find our overall rate of reaction and convert it to whatever species I care about. Oftentimes, this is going to be the only colored substance in reaction because it's very easy to follow these things through things like spectroscopy. So one of the things you could do is say, look at the reaction of bromine with acetic acid. So this will essentially reduce the bromine to bromide, and again, producing some CO2 and some protons. So what we can do is, since bromine is a nice brown and everybody else here is colorless, and sometimes even a gas, we can essentially just track the change in concentration of bromine. So the rate of the reaction can essentially be given by the change in the concentration of bromine over time. So what we can do is measure that change in concentration over time. Now, here's the fun part, is that a lot of reactions don't have a nice linear change of concentration with time. So if I'm trying to figure out my rate, every single point in time will have a slightly different rate. So what we can do is try and find the average rate change over a given, say, in this case, about 100-second period, where I go ahead and I figure out my value at the first point, my value at the second point, and again, take the difference in time. Usually the best way to try and use this method to estimate the time is take the average time, go say 10, 20 seconds one way, other way, find that difference in bromine and time, and you'll get the average rate over this time interval. However, as you may note, that still wouldn't be the most accurate method out there. So one of the things that it's often done is if you shrink that time period till it's smaller and smaller and smaller, you'll get a much better idea of the rate at any given time, and thus you can see how that rate could change. And what you can do is bring this difference into an infinitesimal change. So it's the rate of change in less than a second and measuring the change in concentration at time. This is most easily done by just taking the line tangent to the curve. So again, find the curve at that point, draw a line that's perfectly in line with the slope at that point, because again, the slope is the rate. We can do that at each of our given points in time. Well, for those of you who are familiar with calculus, this is the same as taking the first derivative. So we can try and fit this general change in concentration to an equation, take the first derivative, and ta-da, you're going to get the rate. And this is a big feature here. So of these essentially instantaneous rates, one of the ones that's most relevant that we'll be talking about a fair bit later is the instantaneous rate at t0. So essentially, if I had this curve, I'd find that first derivative at a time of 0, and this is known as the initial rate. However, one of the things that is worth noting here is that as we track this reaction, the rate is changing with time. So in this specific case, as time goes on, the rate slowly ends up decreasing. And one of the reasons why is it turns out that a lot of reaction rates are going to be concentration dependent. So as the amount of the reactant decreases, so will the rate. Our big goal is trying to figure out what is a good equation that represents that sort of behavior. So next time, we're going to be looking at rate laws and concentration dependence. Until then, take care.